Can you all hear me?
Yeah, I can hear you.
All right.
Yeah.
I still got a few people signing on. Give them a minute.
Hey, Ron, I see where we can upload the quiz, but I'm not actually seeing anywhere to access and see the quiz for the take-home quiz.
Let me check that. You can see. Okay. I think that quiz was passed out in class. You don't have a copy of it?
Yeah, I don't have a copy of it.
Okay. I'll scan it and put it on Blackboard. I got my scanner working, so I can go ahead and scan stuff to Blackboard now. Let me see how many people are logged in. Okay, we're going to go ahead and start. I wanted to, you guys got the announcement. They're going to do some work on this app that I use to do these videos. So I wanted to go ahead and do the lecture today. I figure right between the two lab times, hopefully most people will be free. But if not, I'm going to record this. It's being recorded now and go up on YouTube, and you'll be able to see it later on. Let's see, later tonight I'll post the exam 2. So look for that. I'll give you 1 week to complete it, and you'll be able to upload that to Blackboard. And I'll check on the quiz if you don't have a copy of the take-home quiz. I don't know what due date I put on it. I'll check when I finish this, and I'll post it to Blackboard. You can go ahead and work on that. I did get a couple people that text me. I think most people got the multi-sim to work. There was a few people that sent out texts or emails saying they didn't get it to work, and I posted that lab, but then it's been probably almost a week, so you don't want to wait till the last minute to do these labs. I wanted to get the multi-sim downloaded to see if there were any issues, so I gave you a long time to do it. The next lab you're going to do is series circuits. I think I believe there's copies on Blackboard, but the series circuit lab, you'll do that in multi-sim. But I'll put an announcement up about that. Make sure you have pen and paper today. I want to do one more method to solve networks or circuits with multiple power sources. We looked at superposition. We looked at mesh analysis. Today I'm going to look at a method called nodal analysis. So you'll need pen and paper. If you don't have that, grab a pen and paper. And I have a problem over here on the board. I have a resistor. I have a 10 ohm resistor. I know the voltage on one side of the resistor is 20 volts. On the other side is 15 volts. I want you can probably do this in your head, but I want you to write down the steps to finding the current. So get a piece of paper and work this out step by step. I want to know, what is the current flow through the resistor? How much current is flowing? And I'm interested in the steps you go through to get the answer. So go ahead and work that out for me. And then let me know what you come up with. Anybody got an answer for me? What's the current flow through the 10 ohm resistor?
0.5.
0.5 is correct. So the current is 0.5 amps. Now, how did you get 0.5? What did you do?
I found the current with 20 volts and the current with 15 volts, and then I subtracted them, like the difference between.
Is that Kevin?
Yeah.
So you did, but what he did was superposition, and that's okay. I mean, you can do it like that. But there's a more direct way to do it. How would you do it a more direct way? What would you do? Any ideas? What would I do?
I just subtracted I just got the voltage drop and divided it by the resistance.
Okay, so I think that was Steve. Steve said he got the voltage drop. I have 20 volts on this side, 15 volts on this side, so there was a drop of 5 volts. And then he took the 5 volts and he divided by the resistance, used Ohm's law, and got what Kevin got, 0.5 amps. So what he did, he took the voltage over here to 20, subtracted the voltage on the other side to 15. That difference is 5, and then he took the resistance and divided by that voltage drop of 20 minus 15. I want you to remember this. This is how we get current. If I know the voltage on one side of the resistor, and I know the voltage on the other side of the resistor, I can subtract those two to get the voltage drop, and I can divide that voltage drop by the value of the resistance, and I can get the current through that resistor. This is based on this calculation, finding current like this. So I want to show you how you would do that using a method called nodal analysis. So let me erase. Make sure you have pen and paper because I'm going to give you the steps. I'll just say them, and then we'll do it. We'll do it on this problem, and then I'll give you another problem to practice with just to make sure you got the technique. So write this down for me. This is a method of nodal analysis. And again, if you go read it in the book or you look at YouTube, it's the same thing. They may say it in a different way. So just kind of follow what I'm doing here. The first thing you want to do is identify nodes. So you want to mark and identify the nodes. Mark and identify the nodes. The second thing you will do is you will pick or name a reference node. Pick or name a reference node. And then the next thing you'll do is you will assign currents into and out of the node. Assign currents into and out of the main node. And then what you will do is you will write a Kirchhoff's current law for the node in question. And you'll write it in a way that makes sense. Now I got to explain to you what I mean by in a way that makes sense. And then the last step, you will solve for current in terms of voltage. You will solve for current in terms of voltage. So let me go through that again, but I want to show you on this problem right here. Now, this problem should look familiar because we've done this twice. We use superposition to solve this problem. We use mesh analysis to solve the problem, make sure that they agree, the two methods agree. So now I want to show you on the same problem that we can solve it another way using nodal analysis. Superposition advantage is it's very intuitive. Disadvantage is you got to draw a whole bunch of pictures. Mesh analysis is you don't have to draw all the pictures. The problem is with mesh analysis is it's not intuitive at all. Those loop currents don't really exist, and it almost seems like magic. Well, here we have another method, nodal analysis, and we'll see which one of the three methods you like better, and we'll see if this has an advantage or a disadvantage. So, if I want to solve this using mesh analysis, what I do is identify the nodes. There's two of them. There's a node here and a node here. Remember, we define the node as if I have wires crossing, if I circle this, if that circle's cut in at least three or more places, then I got a node. So I actually have a node right here. There's a node right here. Let me try to read it. So I got a node here. And I got a node here. So the first step is to identify and name the node. So I'm going to call this V. This is node V. had another node, I could call it VA and VB. But I got V as my main node, and down here it's called my reference node. So to show it's a reference node, I'm going to put the ground symbol down here. So remember, this symbol is ground. So what that means, reference node means that if I have my black lead and my red lead on my meter, my black lead goes at the reference. I'll keep it there, and I use my red lead to measure the voltages in the circuit. So a reference means I'm going to take my black lead, hook it there, and I'm not going to move it. So everything will be with respect to that point in the circuit. So I've identified my nodes. I've named it. I call it node V. I've identified one node as a reference node. I usually just stick that one on the bottom. And now what I'm going to do is assign currents into and out of node V, that's the main node, in a way that makes sense. So what do I mean when I say in a way that makes sense? Well, I'm just going to arbitrarily assign current directions. I'm going to say that the current in R1 is flowing like this. And remember, you always name a current after the resistance. So this is R1. This current right here, we're going to call that I1. And I'm going to assign the next current like this. That's R2. We'll call this I2. So I said we're going to assign currents into and out of the nodes in the way that makes sense. And what I mean by that in the way that makes sense is, well, if I have I1 flowing in this way and I2 flowing in this way, I3 has to flow in this direction out of the node. It wouldn't make sense to have it going into the node. This would work if you did that, but it's a little easier to think about if you just assign the currents in the way that makes sense. So if I have current going to the left side of the node, current going to the right side of the node, it's got to come out somewhere. It's got to come down through R3. So that makes sense to me. So I have the circuit. I've identified my nodes. I named my node V. I've assigned current directions in the way that makes sense. The next thing you're going to do is write a Kirchhoff's current law equation for node V. Who can tell me the relationship, for the way I have this drawn, what's the relationship between I1, I2, and I3? What's the relationship? Anybody? How are they related mathematically?
I1 plus I2 equals I3.
Can everybody see that? You got, I mean, it's crystal clear. If I have current going into the node here, I1, current going into the node here, I2, it's got to come out. The sum of those two have to equal I3. So I write it like this. I'm going to say I3 equals I1 plus I2. And there's my KCL. The final step of this is now I'm going to write current I3, I1, and I2 in terms of resistance. You already did that. At the beginning of this talk, I asked you if you had a resistor and you knew the resistance was 10 ohms, if the voltage right here was 20 volts and the voltage on this side was 15 volts, right away you can see the voltage drop is 5. 5 volts divided by 10 gave you the 0.5 amps. But I asked you to remember the steps. You took the voltage over here, which was 20, and the voltage over here, which was 15. You took the difference between those two numbers and you divided by the resistor value, which was 10. And that's how you got the 0.5. We're going to do exactly the same thing for each of these currents. We're going to apply this logic right here for I3, for I1, and for I2. The exact same logic. So see if you can follow this. Now I'm going to move this. Let me move this down a little bit. So we got I3. All right, so I1. What I can do for I1 is I can take the voltage. Remember, this is my reference node, so my black lead goes here, and I measure with my red lead. I'm going to take the voltage on one side of the resistor. Well, if you look over here, if my black lead is down here at the reference node, and my red lead is on this side of that resistor, I'm across 84 volts. And it's not just 84 volts, because the way my black lead is down here at the plus sign of the battery, it's actually going to read a minus 84. If I wanted to read a positive 84, since the negative sign is up there, I would have to reverse my leads. But since I have the black lead at the reference node and the red lead over here on this side, I'm across negative 84 volts. So I'm going to take negative 84 minus the voltage on the other side of the resistor. So if my black lead is here, I put my red lead over here, the voltage on the other side of the resistor, I don't know what it is, we call it V. So I'm going to call it V. If I knew the value of V, I can find the voltage drop across the resistor, just like I did when I had the 20 volts and the 15 volts. I don't know, so I'm just going to call it V. I'm going to divide by the resistor value, which is 12. So this is actually pretty simple. You figure out where your reference node is, find the voltage on one side of the resistance, the resistor with respect to the reference node. In this case, it was minus 84. The voltage on the other side of the resistor, we called it V, so it's an unknown here, V. And you divide by the value of the resistor, that gives you the current I1 if you knew V. Now you do the same thing for I2. I2 equals, again, I take my black lead and put here, my red lead is here, I'm across 21 volts, but since the battery is flipped upside down, it's going to read negative 21. So on one side of the resistor, I got negative 21, minus, on the other side of the resistor, I got V. I named it V. So it's negative 21 minus V divided by the resistor value, which is 3. So I got this one for I1, I got this one for I2, and I need one more.
Excuse me, sir.
Yes, sir.
The I1 is negative 84.
It is. Well, it's negative 84 minus V.
Okay. Because I
See?
I'm not see well.
You can't see. You don't see why.
I'm not see well because the light.
Oh, okay. I see. Let me move this down. So we had, I think down here at the spots up there. So we had I1 is minus 84 minus V on 12. And we had I2. And what I did for I2, again, I take my black lead and put here, my red lead and put there. I'm across the 21 volt source, but since the battery flipped over, it's going to read a negative 21. So I had a negative 21 minus the voltage on the other side is V, divided by the resistor value, which is 3. So it's always the voltage on one side minus the unknown voltage divided by the resistor value. Voltage on one side minus the unknown value divided by the resistor value. So there is I2. You see if you can figure out how to write I3. How would I write I3? Well, you do the same thing. You put your reference lead here. You take your red lead and put here. So I'll read the voltage V. So I3 would be V minus the voltage on one side is V. And if I put both leads at the bottom, then that's going to be V minus 0, because the reference node, if I touch my leads together, it's going to read 0 volts. So it's V minus 0 over 6, or just V over 6.
I got a question, sir.
Go ahead.
Why you don't use I3 equal I1 plus I2?
We are. That's the next step. But before you do that, you got to write the currents in terms of V. And you'll see why in just a second. So the question is, when are we going to use, or why don't we use, I guess you can see right here. We said the current, the KCL for this was I3 equals I1 plus I2. I think that's what the KCL that Steve gave us based on the current direction that we chose. So here's the KCL, Kirchhoff's current law for node V. So what would the next logical step be? If I got the current law and I got I1, I2, I3 in terms of V, the next logical step would be to do what? We're going to substitute for each current what we set each current equal to. So we're going to substitute for I1 minus 84 minus V on 12. We'll substitute for I2 and I3. You go ahead, since you have more room than I do, substitute each of these currents for the correct current and the KCL above. You go ahead and do the math for me. Write it out. I'm going to clean this up a little bit while you work on your math. And I know you can't see this. This is just for me, so I can erase the board. All right. So what I want to do now is substitute for I3, I1, and I2. Well, I3, we said that was V over 6. So this is V over 6 equals I1. We said that was minus 84 minus V on 12 plus I2. And I2 is minus 21 minus V on 3. So now you can see the magic of this. We've taken our KCL, we've done a substitution, and now we only have one unknown value in that equation, V. You solve that equation for V, stick the answers back into the original definition for I3, I2, and I1, and you got your answer. So go ahead and solve this for V. However you would solve it, go ahead and solve for V. And let's see what we get for V. And then what I'll do is I'll give you another problem to see if if you caught on to what I with the steps, and then really that's all I want to do today. So I don't know how you would solve this, but I don't really like working with equations with fractions in it. So I'm going to clear this by multiplying each side by, I guess the common denominator is 12. The greatest common denominator. You do it whatever way you want to do it. I'm going to multiply through by 12. If I multiply through by 12, I get a 2 here, I get a 1 there, and I get a 4 there. You get a cheer, guys. All right, so if I clear the parentheses, I get 2V. For that one, I get equals minus 84 minus V. And here I have, I got a 4 times minus 21. That's another minus 84. And I got a 4 times a minus V. That's a minus 4V. So you look at that, make sure I get my arithmetic, my algebra right. I think I did. And if I did it right, we have to combine like terms, and then we'll solve that for V. I get 2V. Now I got a negative 5V right here. If I move it to the other side, that'll be a positive 5V. That'll give me 7V on the left is equal to minus 168. So one of you guys solve this for me. Tell me what V is equal to. Let me know when you got a value.
Negative 24.
Somebody said negative 24 volts. So now we got a value for V. We know V is negative 24 volts. So to finish it up, what you'll do is you will go back to the original definitions that you set up for I1, I2, I3, and we'll just substitute in here for V, and we got our answer. So I'm going to clean this up. So you can see what I'm doing. So originally we said I1 was minus 84 minus V on 12. Well, now we know that V is a minus 24. So what do you get when you take 84, or negative 84 plus 24 divided by 12? What do you get?
5.
Yeah, I got 5.
You get negative 5. Negative 5 amps. What's the significance of a negative current?
It's floating in the other direction.
Right. We assume that I1 is going from left to right. We just flip it around. It's actually going the other way. So I1 is flowing this way, and it is 5 amps. Now you do the same thing for I2 and for I3. See what you get for that. You get I2 is minus 21 minus 24 divided by 3. And that's going to be 1 amp, right? Is that right?
Yeah.
That's a 1 amp. So we know I2 is 1 amp. It looks like we chose the right direction for that. So I just put in 1 amp. And then the last one is I3. So we got I3 equals V over 6. But I now know V is a negative 24. So 4, a negative 4. So that means I got to flip this around.
No. I3. Take another way.
Do what?
Because
I3.
I3 gets inverse because both of the batteries are swapped downward. So wouldn't the electronic flow go from the bottom to the top then?
You don't look at the circuit, you look at this. Do we get a negative current? Right? We had I3 was V over 6. And you told me V was negative, what was negative 24? So that's going to give me what?
Negative 4 amp.
Negative 4 amps. And, I'm looking at this. So instead of going this way,
Yeah.
I got to flip that up the other way. And so I got 4 amps going up instead of down. Now, somebody mentioned something about the negative sign. And I think I mentioned that in class where you really can't, when you have these multiple sources, you don't really know what's going on. The only way to see the actual direction of current flow is to do superposition, to see where the current is going for this one. But when this is added to the circuit, that might upset that. It might change that current direction. It definitely changes the amount. But you guys already have the solution to this circuit. Look back at your notes for either superposition or mesh analysis and see if these answers match what we got the other day when we solved this circuit using mesh. Did we get a 1 to the left, a 5 to the left, and a 4 going up? Is that what we got, or did we get something else? Anybody have their notes? I think if you look at your notes, you'll find that this is the same. We did it 2 other ways. This is the same current magnitudes and directions we got. Now, when we solved this circuit using mesh analysis, it was more complicated. Remember we had to do determinants. We had a 2x2 determinant. We did superposition. The math wasn't that difficult, but you had to draw a bunch of pictures. Here we end up with basically one equation and one unknown, just the v. We solved for v. And we got our answer right away. So I think for this problem, if I had my choice probably would be nodal analysis to solve this instead of the other 2 methods. I might use superposition if I wanted to know the actual current direction for each voltage source. If I had a reason to want to know that, I would use superposition. If I'm just looking for the net current flow through each resistor, this is the choice of my method for this particular circuit. So hopefully that makes sense to you guys. Anybody have any questions over this circuit?
Yeah, sir. If you have a pre-generator, we can use this method, nodal analysis.
If I have a what? What'd you say? If I had a what?
If you have 3 generator.
If you have 3 voltage sources?
Yeah, voltage source. You can use this method.
Yeah, so you're saying, let me make an example of what I think you're asking me. So you're saying that maybe I did something like this. I might have an R4 in there. Is that what you mean?
Yep.
Okay, so if I have something like that, then what will happen is now you got 3 nodes. You got this node, you got my reference, and I got another node right here. So I can't call it V, so maybe I'll call this one VA and this one VB. But it works the same way. You assign your currents, but this time you got to do it for each node. If I had more than the one node that I showed you, and I didn't want to get into this, I just wanted you to see the method first, but since you asked, this is the way you would do it. I would assign a current direction into and out of the nodes. So I might say that I1 is like that. I might say that, I don't know, I can do the same current directions. I2 is like that. I3 might be like that. And then here I might say that, well, I already got I2 defined there, right? So I might say that I4 is like that. And maybe this I can just flip a coin on. I'm going to say, I don't even know what to call that one. I4, I guess I5. I don't have a resistor I5. So, but now what I'll do though is I'll end up with this current right here. This current, let's do one of these. I'll do one. I don't want to do the whole thing. But let's say I want to find I1. Now look at how I would write that. I1. I hope I'm not confusing. I wanted you to do a practice, but he asked the question, so let me just show you this real quick. The voltage on this side is still negative 84 minus VA. But when I get to, minus VA over, over 12. But the trick here is when I get to this current, I2, When I take the voltage on one side of the resistor, I get VB. So I2 is going to be VB minus VA over 3. I still do the same kind of thing. I take the voltage on one side of the resistor, minus the voltage on the other side, and I divide that by the resistor. The thing is here now, if I have more than one node, I'll get 2 unknown values. So I'm going to end up with 2 equations and 2 unknowns. And you can use determinants or some other method to solve that. Now, I'll just tell you right off, though, when I'm doing nodal analysis, at least for you guys, I want you to know the steps. I'm not going to give you one with more than one node. I would feel fair, it's fair for me to do that. The only problem with this is you end up with fractions, and your determinants will have a lot of, if you use determinants, it'll have a lot of fractions in it, and then you end up with a lot of errors as you go through. So I tend to just have you prove to me that you know the method, and then I give you an equation like, a circuit like the one I just gave you with just the one node. But you can do it with 2 nodes. You can even do it with 3 nodes. And there should be an example in the book of how you would do it, at least with 2 nodes, I'm sure. So yeah, you can do it. You just end up with an extra unknown value here. You have to have 2 equations and 2 unknowns to solve it, which if you work this out, that's what we would end up with. But what I want you to do, I got a little less than 25 minutes. Let me give you one to work, and I want you to work it all the way through, and then we'll do it quickly to see if the answer that you get agrees with what I'm doing. So on your paper, copy this down. I'll make it exactly like the one I gave you before. I just want you to get the steps down. Let me see what values I have. Okay, this is 47. This is 82. And this is 22. This is R1, R3, R2. 10 volts. Notice the batteries are flipped now. I flipped them over. 5 volts. And there's the circuit. So go ahead and go through the steps. Identify your nodes. Name them. Get your currents and let me know what the equation is that you got. All right, so this is V. Here's my reference. I'm going to assign current directions just like I did before. I1, I2, and now I'm going to make this is I3. I3 and I2 is right here. So there are my current directions, and you go ahead and write the KCL for that. That's what I got for mine. And then for the final part of this, you figure out each current, I1, I2, and I3, in terms of V and R. V and R. Tell me what to write for I1. What's the equation that you got? Or the I1 is what?
I1 is, okay, go.
You tell me step by step what to write. If I measure over here,
I1 is,
how much?
I1 is 10 minus V over
10
minus
V.
V over 47.
Does everybody see why this is correct? That's right. If I'm over here, I'm across 10 volts. In the last circuit, the battery was upside down, so I measured a negative 84, but in this case, the battery was right side up, so I'm actually across a positive 10. So he correctly said 10 over here minus V divided by 47. That I'm good for I1 and I2. You do the same thing. It's going to be 5 minus V on 82. And then what about for I3? Well, that is I3.
So I3, yep.
That is I3. What about for I2? How much is that? On the top here, I'm across V volts, so just V minus, but down here, 0. V minus 0 is just V over 22. So there are all my currents in terms of voltage. And you just stick those into the equation, solve for V, and then we're good to go. So go ahead and start working that out. I'm going to put these up here so I can keep track of them. All right, so if we substitute for my currents, I got V on 22 equals 10 minus V on 47 plus 5 minus V on 82. And there's my equation with only V's in it. So I'm going to erase this to make some room. Oop, I didn't want to erase that. And go ahead and work that out. I don't know how you guys solve something. I don't know how you guys solve something like this, but whatever method you use to do it, go ahead and do it. This was I2. Okay, so we got, let me move this up a little bit. All right. So we got to solve this, and it's got those nasty fractions in it. So I don't know how you guys solve something like this, but what I like to do, I'm not even going to try to figure out a common factor, it'll take too much time. I'm just going to multiply everything, every term. I'm going to multiply every term by 22, by 47, by 82. I'm just going to multiply all these together. That'll give me a common denominator. So I'm going to multiply each one of those, each term by that. So we multiply this by 22, 47, and 82. Multiply this by 22, 47, and 82. And I'll do the same thing here. 22, I might be in the light there. Let me put that on the bottom. Sorry I don't have a bigger board, so this is going to be kind of out of order. But I'm doing the best that I can do, considering what I was given. So this will give me a common denominator, so I'm just multiplying every term by that common denominator. And if I do that, it makes it a little bit easier to handle. Because that'll cancel, this 22 will cancel with this. So this will cancel with that one. This 47 will cancel with that. So I end up with this 47 canceled out. And that 82 will cancel. I got 47 up here twice. This should be an 82. And that 82 and that 82 will cancel out. And I'll have 22 by 47. So I cleared all the fractions just to make it a little easier. I don't know if that's easier for you or not. But now we got to deal with these products right here. So I don't have a calculator. You guys will have to help me with the math. So somebody take 47 times 82. Let me know what you got. 47 times 82.
38, 54.
38 what?
54.
54 V from here. And then take 22 times 82 times 10. Let me know what that is. Twenty-two times 82 is what?
1804.
1804, so it's 1804 times 10 will be that, right?
Yep.
And then I got to multiply by V, so I get minus 1804 V. And this is going to be confusing because I got to continue this on another line. But now I got 22 times 47. What's 22 times 47?
1034.
1034. Then take 1034 times 5. How much is that?
5170.
I got 5170 minus 1034V. Now, hopefully you guys can see this is all one line. I had to wrap it around like this. But you go ahead. I don't want to do any more arithmetic on here. I don't know if I'm confusing anybody doing this. But go ahead and solve for V. Give me an answer for V. You know how to do the algebra. I don't have to do the work on the board. Solve this for V and let me know what you got. We got about, I think the session cuts off at 3:30, so we gotta get this done in like 6 minutes. Give me an answer for V.
Is it 0.043?
0.043 for V?
Yeah, that's what I got.
I don't think that's right. Somebody recheck that math. We can work it out. I was just trying to spare you the details. So add up,
3.46.
what'd you get?
3.46.
Yeah, I think that's what I got earlier. 3
Yeah,
point,
3.46.
okay. Does everybody see, do we need to work it out? Kevin, do we need to work it out?
Yeah, we good.
You got it?
Yeah.
Okay. So this is right. So now go in, and since we know the voltage is 3.46, we said I1 was 10 minus V, but V is 3.46 over 47. So give me the value for I1. How much is I1? You give it to me in milliamps, I guess it might be better.
0.30. 30.
0.
13.
Oh,
One
okay.
three. 1 3.
Okay, so we're saying that's 130 milliamps. 130 milliamps. And it looks like we chose the right direction, so we're good there. So let's do I3. Can I erase this? Everybody see what we're doing?
Yep.
I3 is 5 minus V on 82. And we said that this was 3.46 volts. So give me the value for I3.
0.01.
0.01. So 10 milliamps. Is that what we were saying? 10 milliamps? And it looked like we chose the right direction for that. So, well, if that's the case, then I2 has to be what? 140? If this is right, it looks like it's going to be 140, but let's go ahead and see what we get. I2 is
0.15.
3.46 on, what'd you say?
0.15.
1.5?
Yep.
150 milliamps? We're off a little bit because you're saying that you're saying this is 150 milliamps. That's not adding up. I get 140. So did we make a mistake? You said that I1 was 130. If this is 10, this should be 140. Or we made a mistake in our calculation somewhere. So we need to go back and.
I found I1 139 milliamp.
Okay. 139 makes it a little better. 139 for I1?
Yes, 139. And then I3 18 milliamp.
This is 18?
Yes, 18 milliamp.
Okay. And then what would this be?
And then I2 equals 157 milliamp.
Okay. That's a little better. Now, I didn't work this out. I started doing what, then the clock caught me. So you guys check these numbers. Go through, check the numbers. I think some of you get lost in the algebra, but it shouldn't be too bad. But this adds up. That's a little closer. And that's about 40. That's about 20, and that's almost 160. So I'm satisfied with that. But you go back, watch the video, and go back and make sure the numbers, maybe some of you rounded or whatever, I don't know. But these numbers kind of feel a little bit better. So what do you think? Which one do you like best? We looked at superposition, we looked at mesh, and this is nodal. Which one do you like best? Do you have a favorite? Anybody have a favorite?
This one.
You like this one?
Nodal is better.
Okay. So I don't know when. I'm going to put the exam up, exam 2. Somebody sent me a text saying that they were a little concerned about exam 2. They didn't know what was going to be on it. It's a take-home test. I mean, you guys are at home, so you got your notebook, you got whatever you want to use. So I'm going to ask about, I'm going to give you a series circuit, I'm gonna give you a series parallel. I'm gonna give you a parallel. Just show me that you know how to work it. And I'm gonna give you one with an unknown value. We did a couple of those. I'll ask about ampere rating, and I'll probably throw a Thevenin in there with maximum power transfer. And then you'll have a few days to do it, maybe a week to do it. I don't know. So look for that today. I'll have it up sometime today. I'll send an announcement out. And if you have any issues, let me know. I'm also going to send out a link for the next lab, which is, I forget the number, but it's the one on series circuits. You'll build that in the multi-sim. Send that to me like you did the multi-sim lab. Anybody have any questions before I turn this session off? Okay.
What about
guys,
the
Just the
what about
quiz.
the take-home quiz?
say it again.
What about the take-home quiz?
Oh, is that Jalen?
Yeah.
Yeah, so somebody, I think it was Sam, didn't have a copy of it. I got the link for it, but some of you don't have the paper, so I'll go up there right now. I'll scan it. I'll put that on Blackboard. What does it do? Is the due date is when? Anybody know when I set the due date for?
No.
Nobody
I
knows?
haven't set a due date yet since the corona started.
Well, let me look at what the due date is. I don't know when it's due, but I may have to adjust that. If you didn't have the test, then I don't, you may need more time. So give me about 30 minutes. I'll put that up, Jalen. And anybody else is missing that, you can get it off Blackboard. And I'll send out a again.
And about the lab work, and am I still able to can I at least send the links to the lab homeworks that I've been doing?
Well, you're in section 2. I think I extended your time. You should be able to still use the link. In session
I'm
1.
talking No, I'm talking about for lab 4 and lab 5, those two labs.
Oh, yeah, I don't know. Let me, you sent me that in an email. Let me, yeah, I tell you what, you may have to email it to me because I don't have, my Blackboard's not set up to do I got to do something special in Blackboard to set the PDFs. And let me check. I'll respond to your email, but it might not be the later one today. But just hold on to it. I'll make it so you can turn it in.
All right, then.
Okay, guys. Well, you have a great rest of the day. Stay safe.
Excuse me, sir.
Yes.
I still have and parallel series homework. How can I turn on it?
You want to turn it in?
Yes.
Well, you'll have to you probably have to give me a PDF version of it and email
PDF and then email it.
Yeah, if you'll have to do that. But just send me a text whenever you email it so I can look for it.
All right.
Okay?
All right.
All right, guys. Have a great one. I'll see you later.
You too.
All right.